Okay, hello everybody and welcome back to the video lectures of decision analysis. And now we are in chapter 5, Sophie Sophomore's Fall. And in this chapter we give an example called Sophie Sophomore's Fall, and the idea is that this will help you with your first assignment, your fall, that is given in chapter 7. So pay attention and uh, watch this video carefully multiple times if needed, so this then doing some obvious modifications, you will get your own first assignment done once you vary or make a variant of what happens here. So in this section 1, we give the problem description, we define the decision matrices and decision rules. So what is the story? So also you in your assignment give a backstory, what your exercise assignment is all about. So here we have a Sophie Sophomore, that's a second year technology student at the University of Vaasa. It is February and Sophie has to decide what to do in the next fall. And what affects Sophie's choice is there is a pending koala Ebola pandemic. So now we encounter again our koala Ebola. So far the koala Ebola has been encountered in Australia, but unfortunately Australia is a popular tourist attraction and the koala Ebola has penetrated the entire country. Australia has not enforced any kind of quarantine yet, so it may be a matter of time before we may have a global pandemic at our hand. So, what does Sophie Sophomore intend to do? So, she contemplates between the following 4 alternatives. So, A1, student exchange to China. A2, concentrate on her studies in Vaasa full time. A3, mostly studies and working in a food delivery company in the evenings, a little bit, but mostly studying. And A4, not so much studying, a little bit of studying in the evenings, and working full time for a multinational corporation. So these are the 4 alternatives Sophie Sophomore has to choose from. And what about the scenarios? So Sophie Sophomore thinks that the following binary yes/no questions are relevant to her alternatives. So whether koala Ebola is pandemic or not, that's one question. Another question is universities in distance teaching or in normal teaching, that's another one. And then this, I use quite a lot, this general alternative world economy is in recess or recovery. And now we have 3 yes or no answers, and in principle this gives us 2 to the power 3 equals 8 different scenarios. However, there is this restriction that the distance teaching at the university only occurs if koala Ebola is pandemic. So if there is no pandemic, there is no distance teaching but normal teaching. So this means that we are left with 6 scenarios. So what are the 6 scenarios? First 3 scenarios are for pandemic. So koala Ebola is pandemic, universities in distance teaching, and the world economy is in recess. S2, koala Ebola is pandemic, universities in distance teaching, and the world economy is recovering. So there are 4 for pandemic. Then S3, koala Ebola is pandemic, universities in normal teaching, and the world economy is in recess. And finally, S4, final pandemic scenario is koala Ebola is pandemic, the university is in normal teaching, the world economy is recovering. And then there are finally 2 alternative scenarios where the koala Ebola has been defeated. So koala Ebola has been defeated and the world economy is in recess, is S5. And finally, S6, koala Ebola has been defeated and world economy is recovering. Then we need the probabilities for these scenarios. So Sophie Sophomore will be using a stochastic decision rule. So this means that the probabilities for the scenarios will be needed. In your assignment, if you decide to use non-stochastic rule, then you don't need these probabilities. So it's up to you what kind of rule you use. Here we use a stochastic rule, so we need uh, probabilities for these scenarios. And since it's difficult to say what is the probability that Kuala Ebola is pandemic, we make it as an unknown sensitivity parameter, call it P0. So P0 will be the unknown Kuala Ebola pandemic probability, and then using the maximum entropy principle again, we say that for each Kuala pandemic scenarios S1, S2, S3, S4 are equally probable, so each of them has probability P0 over 4, and then let's say that this S5 and S3 are also equally probable. Against this we don't we have no argument to say why one is more probable than others, so we make them equally probable. So what is left there is 1 minus P0 over 2 for 5 S5, and for S6 the same, 1 minus P0 over 2. So if you then look at these numbers, they sum up to 1. So P1 and P4 are all equally probable, and depending on the unknown probability, P0 is probability for P1 plus P2 plus P3 plus P4, that's the probability of koala pandemic, and then P5 and P6 are also equally probable, so the probabilities are 1 minus P0 over 2. So now we have our alternatives, we have our scenarios, we have probabilities for the scenarios, and next comes the most important part, is this to define the reward or decision matrix. And Sophie Sophomore, so this is the first time we have this phenomenon. So Sophie Sophomore decides to practice multi-objective optimization. So instead of one objective or reward matrix or decision matrix, there are two of them. So let's call them R, and this is superscript, it's not power, R1 and R2. So these are the two decision matrices. And to make things even more interesting, Sophie Sophomore has chosen opposite objectives. So the optimal value of 1 is, is kind of opposite to the optimal value of 2. And what does it mean? It means that the objectives will be R1 will be earn credit points in 1 year, so that this is a maximization type, that's the reward. And then uh, remaining expected time. Sorry, these are not maybe I have made a mistake here. So these are not opposite objectives. So let's see how this goes. Sorry about that. Maybe you should strike this one. So one objective is earn credit points in 1 year, and then there is a remaining expected times to graduation after 1 year. And this remaining time, you should not maximize it, but minimize it. So this is a punishment. So this is a minimization form. And of course, to fix the numbers here, which is the most important thing in this decision matrix technique, it's difficult, so we have, and there is no mathematical formula how to do it, you just have to estimate them somehow, and then there are lots of uncertainty involved in these objectives. And maybe we should have 3 parameters for sensitivity there, but we will not do that. We will estimate the decision matrices and take the values as they are. So no uncertainty parameters will be involved in the decision matrices. I think that the problem is here, I'm so sorry. So this expected time to graduation after 1 year, this is not the objective, but this, no, yes it is. But it's not earn credit points in 1 year, but it's net worth in 1 year. So this here is a mistake. I will soon in the lecture notes you have, this is probably, if I remember, this is corrected. So there are two objectives. So she wants to have as much money in 1 year, and then the expected uh, time to graduation is the other objective. So these are now uh, opposite, because you get money by working, but you get credit points by studying. So you see that there are two competing uh, objectives now. So let's analyze a little bit of the net worth. So this here is wrong. Sorry about that. So the values, the Sophie's decision matrices are based on the following observations. So these are just some ideas that are from which the numbers come from. So during the recession, the living costs are lower. During the collapse pandemic, the living costs are also lower. Living costs in China are lower than in Finland, but in China one must pay rent. In a multinational corporation, last hired is the first fired. So in the recess case, it's possible that you get fired. Working for a multinational corporation increases the cost of living. So this is the kind of general idea. If you have more money, you are expected to spend it more also. And during a pandemic, there is more work for food delivery, because people are guaranteed, so they need food delivered. And also about this net worth, so we assume that Sophie's net worth at the moment is zero, no assets, no debt. So we also assume that Sophie lives for free, her spouse takes care of the living expenses. So Sophie gets student allowance, which is this much. You should update this number. This number is a couple of years old. And if she decides to go to China, there is a 5,000 euros scholarship for that. And the more precise calculations of these matrices we will look at in later videos, example S_SO like Sophie, and they are also listed in the Appendix A calculations. So now at this point, let's just look at the matrices as they are. So this is the matrix R0 net worth. Here are the scenarios. So these first four are pandemic and these are non-pandemic. So pandemic, distances, and recess probabilities. These are the three defining questions for the scenarios. So here are the alternatives, and here are the values. For example, full-time studying means that you will get negative wealth, meaning you have to take a student loan. And full-time working, it means it can get you very much big money, but also very much negative in case these are the recess probabilities where you get actually fired. That's the interpretation. This is maybe easier to understand how these numbers are reasonable. So these are the expected time to graduation, and for example, exchange to China, it doesn't matter what happens, it's 2 years. Full-time working, it really, for example, here it's 5 years. This means that there is no pandemic and no recess, meaning that you get to work full-time and not be laid off, so it will increase the time to graduation pretty much. So, of course, it's important that these numbers are reasonable, but to be honest, I really use the Harrison-Stetson method for these numbers, so I just look something that sounds reasonable for here. Here I was a little bit more analytic. You can see it in the Appendix A for the calculations where these numbers come from, and but these are, of course, if you criticize this method, you can criticize these numbers. Otherwise, the method is solid mathematics. But these numbers, of course, they were just estimated out of my hat, basically. All right, now we have the decision matrices, two of them. So then we need decision rule, or one or many of them. let's just have one decision rules, and this means that for one decision rule for each of the matrices, it means that there are two value functions. And what is the rule? The rule will be expected value rule. So we have two value functions, v1 and v2, and then for the v1 for I is the rewards weighted by the probabilities, and same for the v2. So this means that we are using expected value rule. And sometimes we write it v1 0 at the parenthesis p0 and v2 the parenthesis for p0 to emphasize the fact that both v1 and v2 depend on this Koala-Ebola pandemic probability p0. So to emphasize that p0 is a sensitivity parameter. So we have one sensitivity parameter at the moment. Then another sensitivity parameter arises from the fact that we have to find a compromise between the two value functions v1 and v2. And of course we could weigh them equally, in which case the compromise value functions would be v is 0.5, and this tilde bar here, v bar p0, means that we have to have, whenever we combine value functions, they have to be the same scale. So v bar is a scaled version of v1 and v bar 2 is a scaled version of v2. Okay. Instead of equal weighting, we make the weight w a second sensitivity parameter. So what happens then that we have a two parameter value function v, which is p0 and w. It depends on the Koala-Ebola pandemic, and then the weighting parameter w is both of these parameters are values from 0, 1. So we weight with w the v1 and the scaled version of it, plus the rest of the weight 1 minus w goes to v2 and the scaled version actually of the v2. And just to remind you what the scaling means, of course we have a function that does it automatically, but just in case that you want to remember, so v1 of p bar means a scale, I take the value, I subtract the minimal value and divide it by the maximal value minus the minimal value, and same for the v2. So after this they are in the same scale. Both v1 and v2 bar versions are values from 0 to 1. Okay, so then if this is constant, if we have a 0 over 0 division by 0 problem, then we assume that the value function is equal to 1. So this was the problem setting, and next we look at the solution of this problem. See you in next video lectures. Bye.